Hey everyone, and welcome. Today, we're going to crack a really cool computer science puzzle, the interleaving string problem. Now, it seems pretty simple on the surface, but digging into how to solve it efficiently, well, that reveals a super powerful way of thinking you can use for all sorts of other challenges.
So here's our game plan. First, we'll get a handle on what the problem actually is. Then, we'll try out an intuitive first attempt, the brute force way, and see why it totally breaks down. After that, we'll build up to a much smarter solution using dynamic programming and walk through exactly how it works. Ready? Let's do it.
All right, let's dive right in. Before we can solve anything, we got to know exactly what we're looking for. So what on earth does it mean for one string to be an interleaving of two others?
The best way to think about this is like shuffling two decks of cards. You've got your first string, S1, which is like a deck of red cards, and your second string, S2, which is a deck of blue cards. An interleaving is just what you get when you shuffle them together. But there's one critical rule. The order of the red cards among themselves can't change, and the order of the blue cards among themselves can't change either.
Let's make this real with an example. So say S1 is AABC and S2 is DBBCA. The big question is, can they form this third string, S3? And yeah, in this case they can. If you look closely, you can see all the characters from S1 pop up in S3 in their original order. And hey, same thing for S2. It's like they're perfectly woven together.
So you're sitting down to code this. What's the first thing that comes to mind? Well, probably thinking about it as a series of choices, right? One character at a time.
The logic here is pretty straightforward. You look at the first character of the target string, S3. Does it match the first character of S1? If it does, great. Let's just assume we pick that one, and then we recursively try to solve the rest of the puzzle. But hang on, what if it also matches the first character of S2? Well, then we have to explore that path too. As long as just one of those paths works out in the end, then we've got our answer.
Now, this recursive approach feels right, and, for tiny strings it would probably work just fine, but as the strings get just a little bit longer, this method runs smack into a massive invisible wall. And here it is, an exponential time complexity. What that means is every time we have a choice, take from S1 or take from S2, our tree of possible checks can literally double. This spirals out of control so fast, and what's worse, we end up solving the exact same subproblems over and over and over again down different branches. It is a colossal waste of time.
So here's the key idea. We have to stop redoing work we've already done. If we figure out, say, whether BCC and CA can form BCCCA, we should just remember that answer. We shouldn't have to calculate it ever again. And that is the absolute core idea behind dynamic programming.
To make this work, we need a totally new way to look at the problem. So let's throw out that messy, branching tree of decisions, and instead, let's reimagine the whole thing.
This is so cool. Let's picture a 2D grid. Think of string S1 running down the side and string S2 running along the top. Our entire goal is to find a path from the top left corner to the bottom right. That's it. If we move down, it means we're using a character from S1. If we move right, we're using a character from S2. The path we trace spells out a string, and we just need to check if that path can spell out our target string, S3.
So this grid becomes our little cheat sheet, our DP table. Every single cell in this grid, let's call it DPIJ, is going to hold a super simple answer, just true or false. It answers the question, hey, is it possible to form the beginning of S3 using the first I characters of S1 and the first J characters of S2?
Okay, talk is cheap. Let's actually watch this thing get built with a nice simple example. We'll use S1 as AB, S2 as C, and we'll check if they can form S3, which is ACB.
So we start with our empty grid. The very top left cell represents using an empty S1 and an empty S2 to form an empty S3. Well, can two empty strings form an empty string? Of course. So we mark that one T for true. Everything else starts out as false.
All right, now let's start filling it in. Let's look at the cell for S1's A and an empty S2. This cell asks, can we form the first part of S3, which is A, using just S1's A? Yep, they match, and since we can get to this cell from the valid true cell right above it, we mark this one true as well. Okay, now for the next cell over. This one asks if S1's A and S2's C can form S3's AC. To get here, we would have had to come from the left. Does S2C match the character we need from S3? It does. And since the cell to its left is true, this one becomes true too.
And here's the final move. We want to get to our destination, that bottom right cell. Can we get there from the left? Nope, that's a false, a blocked path. Can we get there from above? Well, the cell above is true. So we just check, does S1's next character, B, match S3's next character, B? Yes, it does. So since we have a valid path, we can mark our final cell as true.
And that's it. That's our answer. Because we found a valid path of character matches from the top left all the way to the bottom right, we know for sure that ACB is a valid interleaving of A, B, and C.
How simple is that?
So we found a really clever solution to this puzzle, but the real takeaway here isn't just about solving this one problem. Why is this whole grid-based approach so important? Well, just look at this. The difference in performance is just staggering. We went from an exponential complexity, which is basically useless for anything but the shortest strings, to a polynomial one. We just have to fill out the grid once. This is the difference between a program that times out and one that gives you an answer instantly.
And the best part, this isn't some one-off trick. This whole pattern of using a 2D grid is a fundamental tool for programmers. It's the secret sauce behind solving a whole family of famous problems, like finding the edit distance between two words, or finding the longest common subsequence in DNA strands. Once you learn to see the grid, you start seeing it everywhere.
So the next time you're stuck on a problem that seems like it has a dizzying number of choices and paths, just take a second and ask yourself this question. Maybe if you just change your perspective, you'll find there's a simple path just hiding in plain sight. Thanks for tuning in.